Next, we move on to the circular motion portion. This is probably the second most challenging part of the class because I know the forces at angles was definitely daunting for people, and I think the circular motion was a little bit daunting too. And I think it was really just a question of keeping things in order. So what I'm going to do first before I even attempt the problem is I just want to kind of outline a couple things. So when we talk about the minimum speed the car needs to make it around a loop, I'm just going to straight up say this right here. Don't use energy. And then here, if we have the hill height of 22.6 and we want to know if the car makes it around the loop, here, yes, we can use energy. And then lastly, when we're talking about normal forces, we're going to use, again, forces one more time. So here we go. Minimum speed. So when we're talking about a car on a loop that's upside down, let's begin by drawing a picture in a free body diagram. So here's the car upside down, and it's going to have a normal force, and it's going to have its own weight. Both of those push it down into moving into a circle. Now, when there is a minimum speed, what that means is that the normal force is almost virtually zero. In other words, gravity alone is sufficient to keep it moving on the circle. And the reason normal forces get bigger is as the car goes faster, you need a stronger force to keep it on the circle, because if you didn't have that force, it would actually break through the track and like fly off in sort of a weird parabola. So I'm going to set up the equation as Fn plus Fg acting together. And let's be clear, we are moving in a circle. That means we're changing direction. The forces do not balance. So we have an acceleration, and just to be clear, this is a circular acceleration. Now we're at the minimum speed, and that tells us that the normal force is zero. So 0 plus mg is going to equal m times v squared divided by the radius. And now I'm going to put in the numbers. So we're going to say here 500 times 10 equals 500 times v squared divided by 6.4. And when we actually isolate that, we're going to end up getting v equals 8 meters per second around the loop. Next, we want to know if the hill has this height, does the car make it around the loop? And we don't use forces here. We're only going to use pure energy approach. So we have a gravitational force or gravitational energy at the top. It's at rest. This is the top of the hill. And then when we make it to the top of the loop, let's be clear, there is a gravitational energy at the top of the loop, and we assume the car is moving, so there is a kinetic energy. I saw a lot of people try to put mv squared over r in this part. Do not mix up your energy equations and your force equations. They need to be treated separately. So we're going to have mgh equals mg, and at the top of the loop, our height is 2r. Careful here, because we're at the top, that's r, and then an additional r at the top right there, plus 1/2 mv squared. Now I'm going to put in my numbers. 500 times 10 times 22.6 is going to equal 500 times 10 times 2 times 6.4. That's going to be 12.8 plus 1/2 times 500 times v squared. And I'm going to go ahead and actually calculate that out. So when we actually calculate that out, we're going to end up getting a speed of 14 meters per second, which is considerably faster than the minimum speed needed to make it. So the answer is yes. Next, we ask, what is the normal force from the car at the top of the loop given this hill height that we had before? So we know V at the top is 14 meters per second, and we're going to use the force approach again. Now we do have a normal force that we're going to calculate. So we have a downward normal force, we have the weight, and so those two forces act together to make the car accelerate in a circle. So we will have Fn plus 500 times 10 equals 500 times 14 squared divided by that 6.4 because I'm using v squared over r for my centripetal acceleration. And that's going to yield a normal force of about 10,312 newtons. So that is our circular motion problem.